Alright guys, let's take a look at the first MCQ. So we want to calculate the combustion of propine, right? Propine is C triple bond C, 3 carbons. So this propine is actually found here. Okay, so we want to find this combustion of propine. Maybe we'll just let this equation, right? Equation be equation 1, which is equation. Then we have equation 2, equation 3. We'll just put equation 1 here on top. 9 bonds plus H plus H to propane. Okay, so this equation, oh, then okay, so we've used up this equation, we'll take it out. Then second equation is your propane getting combusted. Some carbon dioxide. By right, you should balance the equation, but I'm lazy, so I'm just going to write it like this. Once we've used this, we'll cross it out. Last one we have actually combustion of H2 gas. There's 2 of them. You need to put a 2 in front. 5 by 2. Okay, so use this. Okay, then there's just one equation that we don't know the enthalpy change to. So this is the one that we need to find, delta H. So what we need to do is just to come out with the reaction pathway. These two added up together will give you this 2. Okay, so your equation, right, for delta H combustion plus times 6 goes to minus 310 plus 0. Okay, so your delta H combustion, if you press your calculator, would be minus 1940. Okay, minus 140. Right, so that is how you work out for the first MCQ. Okay guys, let's take a look at second MCQ. So we are given 3 equations. They want you to calculate delta H formation for gaseous HCl. So gaseous HCl, yes, you will need formation, right? So you need half 2 gas plus half gas. Okay, so this is your delta H. Okay, so we're supposed to come out with a energy cycle, or you can use the products minus reactants, right? Find the delta H reaction. So I think I will do the energy cycle. Yes. I think the second equation. Yes. Yes. NH4C solid. Okay, so this is minus 6 kilojoules per mole, right? Use it up, we'll say it out. Then the second thing that we can do again with nitrogen, right? Use 1 nitrogen, 3 H2. We'll get 2 NHS plus gas plus Cl2 Okay, so first equation here. Then next, what can we do? We can use 2 ammonia and okay, so the next thing will be we are using our hydrogen gas and chlorine gas straight away to form your HCl. Since we have 2 of them, we need to multiply by 2, yeah? So the ammonia will just bring it over plus 2 HCl gas. Okay, so this will delta H formation 2 times, okay, of HCl. Last but not least, I think we can combine the ammonia and the HCl. 7,6. Okay, so our clockwise versus anti-clockwise, is there a way to do it? Okay, we need to reverse one arrow. Find this and that'll be right, same as this pathway. Okay, so the green pathway equal to the yellow pathway, and do the calculation like this: minus 629 minus 76 2 plus the H formation HCl. Right, so if you go and do that calculation, you will end up negative 92.5, which is C. Okay. All right. So next question, question 7 from JC. This is a dimerization process, which means that you form a bond between two monomers. So you have N on with a single electron and thing here, double bond O, dative bond O. Okay, so you actually form a new bond between the two nitrogens, and that is how you form the dimer. Which of the following statement is true? The reaction is only spontaneous at low temperature, only spontaneous at high temperature, spontaneous at all temperature. Okay, so you notice that all the options talking about spontaneity, so we need to use this formula. Gibbs 3 equals to delta H minus T delta S. Okay, so we can roughly deduce what is your delta H. Delta H is most likely negative because there's only bond forming here. You form one bond. Delta S, right, is negative as well because you lose one more of gaseous molecules. Okay, so negative. So this whole term, right, minus T delta S is negative, negative, which makes it overall positive. Okay, so your minus T delta S is a positive term. Okay, so you will need the second term, right? This second term, minus T delta S, to be big enough to overcome the delta H in order for it to be not spontaneous. Okay, so by default, right, your delta H cause it to be spontaneous. But if your temperature is low, then okay, this second term will become insignificant. Then it is spontaneous. Okay, so but when it's high temperature, then of course the reaction becomes not spontaneous. So B is wrong. C is also wrong. Non-spontaneous, D is also wrong. So our answer is only A lah. Okay, low temperature, then our sign of the Gibbs free energy depend on delta H. Okay, so question 9 from IJC. I very briefly write down whatever the question has said, which is enthalpy formation of CO and CO2. Which of the statement is correct? you can see that actually option 1 is very obviously CO2 will have a lower energy level than CO. So option 1 is correct. Combustion of carbon is the same as formation of CO2. Correct. CO2 is formed exothermically, yes, in order to go from minus 110 to minus 393. This is exothermic. Larger amount of energy to atomize CO2. Yes, because you got to break 2 C double bond O. So if you want to atomize CO2, get 1 carbon and 2 oxygen atom, you need more energy. That is correct. Okay, so our answer is option A. Okay, question 7, you have delta H for this reaction. You're given delta H formation of O2. There's 3 of them. 3 times minus 394. Delta H formation of CO also 3 times minus 110. The other one, iron, has no enthalpy change of formation because it's an element. What's the standard enthalpy change of formation for iron oxide? Okay, since we already know this enthalpy is minus 27, right? Go ahead and do the energy cycle. These two pathway is the same as this pathway. Okay, so go ahead and write out equation. Delta H formation, iron oxide plus 10 plus 7 equals to 4. Okay, so if you use the formula, you get pretty much the same thing. And then basically you just into your calculator, you will get an answer of minus 85. So answer here is D. Okay, so for this question, right, you kind of have to work a little bit backwards because they have given you some data, lattice energy, enthalpy change of hydration of the ions. So if they given you this data, right, you got to go ahead and use this to calculate delta H of solution. Okay, so once you got the delta H of solution, you can use that to work backwards. Okay, you find number of moles from 10.5 grams, which 0.5 moles. Okay, so you take your lattice delta H solution, multiply by the number of moles, you will get your Q, right? Get your Q. And Q is equals to MC delta T. Okay, mass of water is 250. T given as 4.2. Delta T is the one that we don't know, right? Like delta T, the one that we don't question. So we have all the rest. We can find the change in temperature, which if you calculate it, it will be 16.9 degrees Celsius. Okay, since your process, right, endothermic, right? Endothermic, the temperature should drop. Okay, from 30 to 16.9, it dropped 13.1 degrees. Okay, so our answer here is D. Okay, so this question 6 from SAJC is pretty much the same as the one from IJC that we've gone through earlier on. So probably don't need to go through it again. So here is A. Okay, only 1 and 3 is correct. Okay, enthalpy change of combustion of solid is not 2A. Okay, because combustion of carbon, right, is the same value as formation of CO2. Okay, so that value is minus 393. Right, so our answer here is A, 1 and 3. Okay, so let's look at this question from SRJC. I believe this question is adopted from a 10-year series question. So what do we know? We know Gibbs 3, we know delta S, right? At 298, we can calculate your delta H, like a positive 2.1 kilojoules per mole. Okay, this we can calculate from the formula Gibbs 3 equals to delta H minus T delta S. Okay, so once we calculated all the delta H, we can actually put it in energy level diagram. Okay, so your graphite, right? Graphite is lower energy when compared to diamond. Okay, so let's look at the options. Enthalpy change of atomization. Okay, so if you want to atomize these guys, right, you're going to atomize them to the same thing, which is carbon gaseous. So is diamond going to be more endothermic? Looks like no, right? The arrow is shorter here. So first option is out. Enthalpy change of combustion is more exothermic. Okay, because it goes down to the same level, CO2 gaseous. So yeah, it is more exothermic. So B is okay. As in number 2 is okay. Statement 2. Statement 3, bond energy of carbon-carbon bonds in graphite is greater than in diamond. Yes, that is also true because graphite is sp2 hybridized, diamond is sp3. So sp2 has better orbital overlap. Statement 3 is okay. Okay, statement 4, activation energy to convert graphite to diamond is lower than the first. Activation to convert diamond to graphite lower than the activation for, in fact, is higher, right? In fact, it's higher. So if you draw out, you realize that if you go the reverse way, right, the arrow is shorter. Okay, but from graphite to diamond, the arrow is longer. Okay, so statement 4 is wrong. Our answer here is B, 2 and 3 only. Okay, question 14, they want you to find out which statement out of the 4 it doesn't make sense. Okay, so it means that if you look at the enthalpy change of solution for magnesium fluoride, negative, so it is soluble. Okay, but barium fluoride is positive, so it's insoluble. Okay, so if you look through the options, right, option C, the one that doesn't make sense, because if lattice energy is smaller than magnesium bromide, right, it should be easier to dissolve, but it is insoluble. Okay, because if you look at the delta H solution, right, negative lattice energy plus sum of both delta H of hydration. So if you say that the lattice energy for barium fluoride is smaller, so it's actually easier to dissolve, right? But if you see from the observation, delta H is positive, so in fact it's harder to dissolve. Okay, so our answer here is C. Okay, so the last question from YJC. You have this table of data. So basically, you are supposed to do the Born-Haber cycle and calculate the answer. So here is B. Let me quickly show you the Born-Haber cycle. So this here is the Born-Haber cycle. You're supposed to calculate delta H formation in a moment. Okay, so you're supposed to calculate delta H formation. All of these thing. Okay, so just add up all the enthalpy change on the green arrow. That will literally be your answer, delta H formation of lithium bromide, right? So you should get negative 415 kilojoules per mole. B.